algorithm that we will learn today will be about the decision tree and tree-based algorithm. Actually, I would put this way, the reason that we call it tree-based algorithm is because decision tree is like a fundamental level. So the progress of the lecture today, this lecture 13 and lecture 14 will look something like, okay, I'll just show the name. This is lecture 14. So things go this way, like you have decision tree, then you extend it with backing technique. And backing actually have two sub-techniques, not sub-techniques, but it's like evolution of the technique called random forest and boosting. So this boosting, like the random forest itself, become like another technique that people normally use, but I'm not sure how to say this, but it's like at the core of random forest. The core of it is like it came from decision tree. So random forest is built after you know how to say this one. It is like a forest means that you have a lot of trees inside, and actually those trees are decision trees. And actually the objective, like how you want to use it and the application that you can apply with it are the same. Meanwhile, boosting is like a technique to improve the decision tree, and actually for the boosting itself, it also evolved to be some, like a new group of the tree-based algorithm called maybe the gradient boosting. And then so on and so forth. You may heard the name GX boost. And then cat boost. Not sure what does it call, but yes. So boosting itself like become like a root, like become the foundation of other techniques that came afterward. And usually all these techniques are very efficient, very powerful. And these days it is like if you don't have enough data set to train neural network, people usually opt for either GX boost, cat boost, random forest, or support vector machine. And sometimes you would get a better result from this tree-based algorithm than support vector machine, because for one thing, support vector machine assume some kind of hyperplane cutting. But the thing is, sometimes, how should I say, when you talk about hyperplane cutting, it's actually modeling the relationship between samples, like of two class. So it's like the P of X given Y, and you want to see if they are well separated with this. But decision tree will model the relationship between X itself, like the input features, what is the relationship between them. Because as you will see in future, when we make decision tree, we actually use the value of X or input features to create nodes and maybe decide that nodes should be root nodes or should be root nodes or leaf nodes, stuff like that. So decision tree will very much building like a classifier or regression based on relationship between input features. So it's like the main difference between tree-based algorithm and support vector machine. But if you think about what we've done before, like regression, pretty much regression is like model the relationship between label and X. So for regression is like, the linear regression and maybe logistic regression. It is like modeling the relationship between X, Y given X. That is, you have x, and then you put it into the function, and that function is used to infer y. And it's just relationship between x and y. It doesn't go as deep as what is the relationship between each of x, or is whether or not one feature is depending on another feature. It doesn't look at that dimension at all. But decision tree or tree-based algorithm that we would learn today will try to exploit those relationships. And the reason is because sometimes these, input features, they have certain relationship within itself. For example, if we have a patient walking to us, and we use two information to decide whether or not this patient can be released from the hospital. And that two information are the blood pressure and the blood sugar. As you can see, as a doctor, they will start to think whether or not that patient is in a normal health condition, firstly based on the blood pressure. But secondly, they will start to look at the blood sugar. So the condition of whether or not they will look at blood sugar depends on the blood pressure. So that is why we say that with tree-based method, we kind of use the connected relationship between x and then derive the final decision based on those previous decisions that you made. So that is the a main feature of this algorithm, because for other algorithms we don't really try to think whether or not one feature depends on other. Actually, as you can see, the tree-based algorithm would likely to fail if all of your features are somewhat independent of one another. But they may be correlated to your prediction output. For example, if I change my feature to something like blood pressure, I still keep it, maybe height and nationality, those features are totally independent. There's no relationship between them. However, if you can collect enough statistics, you may be having that, let's say people from